So let's let's do some crucial application of uniform boundedness principle. So application of principle to Fourier series. So okay, let me recall first uniform boundedness principle. Uniform boundedness principle. Okay.
Are you writing something?
Oh, nothing is there. Why today my net is not good? Nothing has come there.
No, sir.
Yeah, I didn't. I also don't. I am also not seeing anything. Maybe I will stop sharing and come back again. Usually this internet is good, but I don't know why it's happening like this. So if you don't see something, if you see me writing and if you don't see anything in the screen, you tell me. Okay.
So can you make your tab horizontal?
Oh, you want it that way? Oh, okay. I forgot. Now is that okay? And you want it the other way, no? Horizontal or something. Oh, it's too big. Okay. So anyway, let me recall uniform boundedness principle. So if X is a Banach space, X actually need not be a Banach space. Let me tell you why. Banach space and T alpha in some I indexing set is a family of bounded operators from X to some Y maybe. And if T alpha X norm of this if supreme of this alpha in I is less than infinity for each and every X, okay, for arbitrarily fixed X, okay, for X in X, then this norm is also less than infinity. Okay. I mean, if it is pointwise bounded, then it is uniformly bounded. That's what it says in uniform boundedness principle. Actually, so the converse, so you don't require this X to be a Banach space, even if it is a non-linear space. This is true, and that's because if you have a family of bounded operators, a non-linear space, you can extend it to the completion. So you can actually have the. I mean, in the theorem we need to prove in the proof of the theorem we need it to be a Banach space because we are using bare category theorem. So for there we require completeness, but it's actually not required because any family of linear operators can be extended to the completion with the same norm. Okay, the norm is also preserved. Okay. So conversely, anyway, that's the remark. Let me write the remark. Holds for non-linear space. Non-linear space, general non-linear space. So the converse of the theorem. So converse of the theorem says that if X is a, let's take it Banach space. It's not coming. I don't know. It's too slow. Okay, X is a Banach space. And T alpha be a family of bounded operators on X. I mean, it can be to a different Banach space for the time for now, maybe different Banach space, X to C, X to Y, okay. X, Y Banach spaces. Okay. Then if supremum of norm T alpha equal to infinity, then there exists a X in X such that supremum of alpha in I is equal to infinity. Okay. If it is not uniformly bounded, then there is some X for which it's not bounded. I mean, the family is not bounded. The pointwise it's not bounded. Indeed, this is exercise. See, the bare category theorem says the following: if you have a family, I mean, if you have a family of open dense subsets of a complete metric space, then the intersection of those open dense subset is dense. That's what it says. So, in fact, indeed, there exists a dense family, dense subset D, dense. It's actually what is called a G delta subset. G delta subset D contained in X. Okay, dense G delta means intersection. It is intersection of open set. I mean, it's something non-trivial. See, open set is non-trivial because its interior is non-trivial. I mean, it's not an ordinary set. So a G delta set is a intersection of open sets. So we have a dense G delta subset such that this T alpha alpha equal to infinity for all X in for all X in D. Okay. So even this is true. This holds in a dense subset. So that's what this holds. So this is the converse of uniform boundedness principle. So we want to use this to answer a question negatively for Fourier series. Okay. So let me recall what a Fourier series is, and then we will answer a question that this is about a convergence theorem for the. So the question is the following. This is the application of Fourier uniform boundedness principle to Fourier series. So let's denote something. Let X equal to C 0, 0 to pi. You can take any interval. I'm taking 0 to pi. It is all those continuous function f in C 0 to pi. Continuous function, complex valued continuous function from 0 to pi, such that f of 0 equal to f of 2 pi. The endpoints coincides. So this is something like, I mean, this is equivalent to considering all periodic functions with period 2 pi or functions on the circle in the complex plane. Okay. So it is equivalent to considering, I mean, you can think about it. I mean, it's equivalent to considering those function space. So I'm considering the function space, continuous function on the interval 0 to pi, such that the value coincides on the endpoint 0 and 2 pi. So this is a Banach space with respect to uniform norm. Okay, this is a Banach space. And if you have a f in C0, 2 pi, then define. I am sure you must have seen this Fourier series in the last semester or elsewhere. Then f hat of n equal to integral 0 to 2 pi. There are many versions. You can consider interval 0 to 1, or you can consider minus pi to pi. I'm just considering 0 to 2 pi here. Okay. You can take any interval AB also. Then you need a constant. You have to divide it by, you need to have some constant to, so that the norm is preserved. The L2 norm should be preserved. Okay. For that you need something. So I am just taking it like this, 0 to 2 pi. Here also, I'm not sure whether I have to divide it by 1 by 2 pi to have the norm, but this is okay. Because the question we are going to answer need not have any, I mean, we need not consider those things. Okay. So I think I have to divide it by 1 by 2 pi or something. That's okay. So this is defined by f of t e power minus, so here there is no 2 pi, I n t dt. Okay, I am just integrating the function f of t with e power int. In L2 space, this is just the inner product of the function f with the e power int. Okay, so the f hat is a function. So for n in z, okay, for integers. So f has a function from z to c. Okay, so we had a continuous function and we got a functions on the integers. So this is a discrete valued function. And this Fourier transform is a very powerful technique, both in practice and in mathematics. So if you have, so the thing is this Fourier this is what is called Fourier series, and this Fourier series determines a function. So once you know the Fourier series, you should be able to get back the function. I mean, the question is, where it holds, what are all the functions, we can actually get back the original function, and that's the basic question. And this is a powerful technique used in engineering everywhere. For example, if you consider the digital, whatever we call as digital information, which is a discrete information, so that you get it, you can I think that is what happening in engineering. I'm not an engineer, but if you have a continuous analog information is a continuous information, you have a continuous function which you can convert to discrete values, I mean discrete information by this Fourier transform, then you can get back to that. Okay, so this is very important in many engineering courses also, but they may not really know all this mathematics. They may be using it just like that. Okay, so this is the Fourier series. The question is the following. So once we have this Fourier series, we have a complex number for each n, f hat n. So what happens to this? So this is from n equal to minus infinity. We have a series. Okay, I mean, we had integral there. So we have this is like inverse Fourier transform. We have minus infinity to infinity, f hat of n. And there we had e power int. Here we will have e power int. Okay, this is for each t. Does this converge to f of t? This is the question. Okay, I mean, this is a infinite series. So you need to talk about convergence in which topology and whatever. So does this converge to f of t? Whether, I mean, we would require it to have it for each t. Once again. Yeah. So you can see that this convergence happens in L2. If f is a function in L2, of course, it's a continuous function on a bounded interval, so it should be in L2. Okay, so you can define, so f is in L2. In fact, this C0 is contained in L2, right? C0, 0, 2 pi. These are all bounded function, and it's a finite measure. So this is contained in L2, 0, 2 pi with respect to Lebesgue measure, of course. Okay, Lebesgue measure. I mean, they call it lambda, and lambda is Lebesgue measure. Okay. So you can see that these functions int is a function in t. Okay, n in z contained in L2 is an orthonormal basis. Okay. So if in a Hilbert space, if you have any Hilbert space, then you take the inner product with the, and you call it En. Okay, inner product with En, and then you get a number and you multiply that with En. Okay, you will get back the f. Okay, so you can prove that this is an orthonormal basis using Stone-Weierstrass theorem. I talked about it as an application of Stone-Weierstrass theorem. This e power int, this family of functions, is an orthonormal basis for this L2. We can first prove that it generates the C0, and then you can see that if you take any function in L2, its inner product with all these things, or suppose the inner product with each e power int is 0, then the function itself is 0. So that will prove that it's an orthonormal basis. Okay. So then this is true by the Hilbert space theory. This is true. But then this convergence is not point-based convergence. This is true in L2. Okay. As L2 function, they are same. That means it's almost everywhere. I mean, it's same almost everywhere, and the convergence is in L2. It's not point-based convergence. But if something converges in L2, then there's a subsequence which converges, but then we may not actually get the point-based convergence. So question is, so we have L2 convergence. The question is, does, so anyway, let me define the sum, I mean, partial sum. So if you have f in C0, 0 to pi, okay, then I have this f hat n e power I L T summation n equal to minus L to n. You call this as Sn. Sn f at t. Okay. So this is the notation. This is the partial sum. So the question is, does Sn f t converges to f of t as n goes to infinity pointwise? Okay. We know that the convergence happens in L2, but whether this converges pointwise is the question. Indeed, it's true under some conditions. Like f is in C1, if it is differentiable, if it is, I mean, if it is one differentiable and the derivative is also continuous, then that is true. Or f is generally uniform continuity, I don't know. But if it is Lipschitz, there is something called Lipschitz continuous. If f is Lipschitz continuous, then this is true. So under some condition, this pointwise convergence can be guaranteed. But in general, no. So we are not going to prove this convergence theorem. That is part of any Fourier series. Oh. Sorry, I have some problem with the internet today. I don't know why. Maybe I have to. I'm waiting for it to play. I think you are not seeing. Can you see the screen?
No, sir.
Can you see?
No, sir.
No. Okay, so maybe I will start sharing it again. I don't know why this is happening today. Yeah, I think you can see now. So in general, pointwise convergence is not guaranteed. So that is what we want to prove. So we want to prove the following. So there exists a continuous function. So we are going to prove the following. This is the statement. There exists a function f in C0, 0 to pi such that Sn f at 0. Okay, Sn at t we want to show diverges. Okay, it becomes I mean, it's not bounded. Okay, it's in, so if it is a convergence, if we I mean, for a fixed t, if it is convergent, it should be bounded. It's not bounded. So we will not have pointwise convergence. So that's what we want to prove. So to prove this, we will prove some lemmas and other things. And finally, we will use the uniform boundedness principle. Okay. First thing we want to prove is the following. What is SNF? We want to consider this SNF. I mean, if you have any question, you ask me. I hope I'm writing. I mean, it's fairly clear what I am doing. Okay. So let me write what is this f of t, which is equal to, which is just summation n equal to minus n to n f hat n e power int. Okay. But then f hat n is nothing but integral. F hat n is f of t e power minus I n t, right? Yeah, that is f at n. Sorry, this should be s, right? This I'm going to integrate this. Yes, and then e power int. This is the e power int. And then we have a summation n equal to minus n to n, right? This is what we have. So this is equal to integral 0 to 2 pi. Integral 0 to 2 pi. Integral 0 to 2 pi f of s summation n equal to minus n. I'm just taking the summation inside e power minus I n s minus t, right? ds. Okay, this is okay. Now this is equal to integral 0 to 2 pi f of s. Okay, I change the variable. I change it to s minus t. I call it x or something. S minus t equal to x. So there I have t. So this is just t plus x. Okay, this is okay. So now let us compute this. This is just a geometric series. This is equal to e power. So n equal to minus n means I n x into 1 plus up to e power. So if you want, if you don't see anything in the screen or something, please tell me, okay? Plus e power minus ix, right? Plus up to e power, it should be 2n. So it should be minus I 2n x, right? I mean, this is a geometric series, right? So which is e power I n x into, there are 2n plus 1 terms, okay? So e power minus I mean, e power ix is the, the common factor of the geometric series. So it will be, there are 2n plus 1. So 2n plus 1 x minus 1 divided by e power ix, e power minus ix minus 1, right? I am just using the basic formula, some 8th standard formula of geometric series. I mean, it's not a geometric series, finite series, okay? It's not a series, infinite series. So this, if I just compute it, take it inside, I mean, just to make, not to make mistake, I have just written it like this, okay? So now this is equal to e power, if I take I n x there, then this is going to be I 2n plus 1 minus n, which is just n plus 1, right? N plus 1. Minus e power I n x divided by e power minus ix minus 1. So which we can write it as e power minus I n plus half. Just dividing an e power ix on the both the places. E power ix by 2 on the numerator and denominator. We get this e power I n plus half x divided by e power minus I x by 2 minus e power I x by 2, right? Now this is equal to sine, I mean, this is just two complex number which are conjugate to each other, okay? So which is sine of n plus half x divided by sine x by 2, okay? This is fine. Is this fine? This is what is called dn of x. This is what is called Dirichlet kernel. I mean, this is what is the famous display kernel in Fourier series. Okay. So I have just evaluated what is in that integral. Okay. This thing I have just evaluated. I have just computed it like this. Okay. So these things implies that whatever that SNT, the summation, the partial sum, SNF at t equal to integral 0 to 2 pi f of x into dnx, where dnx is this. Okay, this is dnx. Dnx dx f of x plus t. Okay, f of x plus t dnx. Okay, it's fine.
Yes.
Okay, so this is this is what we have. Now we want to show that this diverges at t equal to 0 for some function. Okay, we don't explicitly produce the function. We will use uniform boundedness principle to show this. Okay, so for that we need the following lemma. The first lemma is limit n going to infinity, integral of this 0 to 2 pi mod of dnx dx. Okay, this thing is equal to infinity. This limit is infinity. So these are all positive numbers. I mean, we have integral 0 to 2 pi of positive function, which is a positive numbers, and this is equal to infinity. Okay, that's what we want to do. This is some computation, which is very standard. Okay, so we want to talk about this 0 to 2 pi mod of dnx dx. Okay. So this is equal to, let me just write the definition. I have it here, so I'm just copying it here. Mod of sine n plus half x divided by sine x by 2 dx. Now we have sine for any x, sine t is less than or equal to mod sine t is less than or equal to mod t. Okay, I mean, you just at 0, both sides are 0, and if you differentiate it, you get, I mean, if you differentiate t minus sine t, you get 1 minus cos t, which is greater than or equal to 0. So, I mean, it's an increasing function that in t minus sine t is increasing. So, sine t is less than or equal to mod t. Okay, so I have said it orally. You just verify yourself. Okay. Okay, so because of that, we have this thing is this is greater than, we want to say something is goes to infinity, limit goes to infinity. They are all positive function, they are all positive numbers. So I take it greater than or equal to 0 to 2 pi sine n plus half x, and I replace this x by sine x by 2 by 2 by x. Okay, by 2 by x. Okay, dx. Okay, so now I change this variable. This is equal to 2 by 2. Let me take the 2 outside. 2 does not matter anyway. It's just a constant. We want to show its diverges 0 to 2. No, 0 to 0 to n plus half. Okay. Sine x by x dx. Maybe there is a k. I don't care. I mean, if you change a variable, you will get some constant. Okay. Let me put just a k, one single k constant. That constant does not matter. So now this is greater, there is an n plus half. This is, I just write it as a summation. This is greater than summation of k equal to 1 to n integral k minus 1 2 pi to k times 2 pi. Now I have sine. Okay, I mean, I put a modulus here. I forgot to put modulus. Okay.
Your screen is updated.
Yeah.
Your screen isn't updated. You can't see what you're.
Right. Yeah, it's coming. It has come.
Okay.
Yeah, there is a lag. I don't know. I haven't paid the internet bill, I think. So they have decreased the speed, I think. I don't know. But there is time. I don't know why it's going on like that. In the month end, I mean, when it's nearing the deadline, they do it like that. I don't know. It's a very good service, but suddenly it becomes like that. Okay. So now it's okay. So k minus 1, 2 pi to 2 pi. Then I want to, so what is it? Yeah, inside I have only sin x by x dx. But then this is greater than or equal to summation k equal to 1 to n integral the same thing, k minus 1 2 pi to k 2 pi. This x is 1 by x. I have 1 by x, so I just put 1 by, I have a k here. I mean, this is a capital K, which is a constant. So I replace it by another k, which is that k by that k2 pi. Okay, I mean the value of x in that other extreme. So then I have just sin x. Okay, dx. This is okay. But this is sin x is integrated between some integer times 2 pi to the next k, I mean some k minus 1 2 pi to k2 pi. And you know that that value is something greater than 1, some number. So all these things is equal to summation k equal to 1 to n, some constant c times k, okay, which goes to infinity as k as n goes to infinity. Okay. I mean, there are some constant which you can accumulate and call a big constant c. Okay, so which goes to infinity as n goes to infinity. So this is fine. Just a simple manipulation. I hope this is okay. So we have that this number goes to infinity. So now we will define a linear functional on x. Okay, this is okay. Now we called our x is equal to 0 to pi. Okay, and define a phi linear functional from x to c by f going to SNF at 0. Okay, which is equal to integral 0 to 2 pi f of t dnt dt. Okay, where dnt is that sign, whatever that function we have defined. Okay, it is that function. So this is certainly a linear functional, and it is a bounded linear functional. Then we have the following proposition: norm phi equal to integral 0 to 2 pi modulus of dnt dt. This integral. Okay, this is our claim in the proposition. So let's prove it. So first, phi of f equal to integral 0 to 2 pi. So this x is 0. So I mean, whatever I had it as, I mean, we are just evaluating the partial sum at 0. Okay, so that's why I have not returned phi of t plus x or something. It is at 0. Okay, so which is equal to f of t dnt. So mod of this equal to mod of this is less than or equal to integral 0 to 2 pi mod f of t mod of dnt dt, which is less than or equal to norm f infinity. You can take the f infinity out. Okay, this is just mod. So this implies norm phi is less than or equal to dt. Okay, we want to prove it's actually equal. So to prove that, see, this is how we usually compute the norm of some linear functional or linear operator. We will first show that I mean, even for a linear operator, we'll first show this. This is some k times norm x. Then we will prove that will imply that norm of t is less than or equal to norm of k. Then we will prove that it is indeed equal to the supremum is attained there. So to show that the supremum is attained there, we have to we can either evaluate on some vector and show that the supremum is attained, or we can have a sequence of vectors which converge so that the txn will converge to that sequence of vectors whose which are unit vector or whose norm is less than or equal to 1, and we will which further the txn converges to that. So we produce the following. So I want the following. I want to produce. Okay, let me just directly write what it is. So let's call En equal to, this is a set T in 0 to pi. Okay. t in 0 2 pi such that we have the dnt is greater than or equal to 0 wherever it is positive. I call this set as en. Okay. Then we can define this d of any this distance function you must be knowing d of s en. For any set you can define en is closed. Okay. This dnt does not look like a continuous function. It is a continuous function, but the endpoints, it looks like something else, but you can see that the limit exists at the endpoints. You can define, see, when x is 0, this denominator becomes 0, but still if you compute the limit, you can use L'Hopital rule, something like you will get half times cos x by 2, n plus half by sine n plus half x or something. But then the limit will exist. If you have cos and cos 0 is 0, so you get a finite limit in 0. And for the other way, 2 pi, sorry, the other, yeah, at 2 pi also you will get, both of them will become, cos of that will become -1. Okay, so this dn is a nice function. Okay, so it's bounded. It's a bounded function. And so this is, and it is continuous and en is closed. Okay. I've given the reason that en is closed. It's a continuous function, and any continuous function, then you can, if you define dnt is greater than or equal to 0, then that's a closed. It's a closed set. Okay. For closed set, we can define it. You must have seen this in some analysis course. For example, to prove Urizan lemma for a metric space, you will use this function. Or if you, I don't know whether you did that in measure theory, if you want to do regularity of measure, if you want to prove regularity of measure, then you will use function like this. Okay. So this is a famous function. In fact, if you want to produce continuous functions and many continuous function on metric spaces, this is one way of producing in arbitrary metric space, is one way of producing continuous function. Okay. So dsn equal to infimum of t in en d of st. Okay. So this is the distance between a point and a closed set, which is well defined. Okay. So this is the infimum. And this dst is continuous. For example, d of st d of s1t minus d of s2t. This, I'm just giving the proof that it is continuous. Okay, is less than or equal to, by triangle inequality, this is less than or equal to s1 s2, right? But then you can reverse the inequality and put a mod here, which will be d of s2 s1. This is symmetric. Okay, so you can put a mod here. So these two things imply that no, you can take one of the infimum. Anyway, you just check this. D of S1 E1 En minus D of S2 En. Okay. You use that, and if you take the mod, this is less than or equal to D of S1 S2. So this will imply that this is uniformly continuous. This function is a continuous function. This is a uniformly continuous function. The D is a uniformly continuous function. Okay. Now using this DSN, I want to define a function. Define Fn. So define Fn of S equal to 1 minus n dsen. Dsen is a continuous function. My 1 plus n dsen. Okay. Notice dsen equals 0 if s is in n. Okay. Hence, fns, if dn is equal to 0, fn is 1 if s is in, this is s. Okay, s is in en. Okay. And so if it is not, see, this distance function is 0, f1 only if that s is in that closed set. Okay. So if it is not in the closed set, then that is strictly not equal to 0. So fns equal to 1 minus n dsen Now DSEN is not equal to 0. Okay, 1 plus n DSEN, which is equal to 1 by n minus DSEN. And this goes to minus 1. Okay, if S is not in EN. I mean, they are not, it's not in the 0 by 0 form. They are strictly not equal to 0. So because of that, it's in, it goes to minus 1. Okay, so we have the following. FNS goes to 1 if S is in EN. Okay, it goes to minus 1 if S is not in EN. Okay. So these things imply use dominated convergence theorem. I will tell you. Dominated convergence theorem. Integral 0 to 2 pi FNS dA. I mean, maybe I should use the capital N. I have been using that. DN. I mean, I was using small n, doesn't matter here. Okay. DNS. So FNS DNS will converge to mod of DNS. Wherever it is negative, wherever see that is how this EN is defined. EN is the set where that DN is positive. Okay. Wherever the DN was positive. EN is the set where the DN was positive. Okay. So wherever it's not positive, that is its complement, and there it becomes like this. Okay. And Dn is a real value function, of course. So it's either positive or it's not positive. I mean, either it is non-negative or it's negative. Okay. Okay. So this converges to, by dominated convergence theorem, this converges to mod of DNS. Yes. Okay. And the norm of FNS is less than or equal to 1. So this norm infinity is also less than 1. For each S, that's less than or equal to 1. That's clear. Because of that, this is less than or equal to 1. So these things imply that, I mean, that is the phi ns. So these things implies that phi of norm phi, whatever we defined as norm phi, that is equal to integral 0 to 2 pi is this fine? Let me recall what I have done. So I have a Banach space C0, 0 to pi, all continuous function taking, I mean, whose the values at the endpoints coincide. Then I define a linear functional, which is the partial sum of the Fourier series, okay, SNF at 0. Then I proved that, I mean, which is the linear functional, Then I proved that the norm of that phi 0 to 2 pi, the DNT, the Dirichlet curve. The norm, the integral of this Dirichlet function. So that's what I have proved. If you have any doubt, you ask me. This is just pure computation. Okay. So I have proved that this is the norm. Now we know that, I mean, this is some for each n we have this linear function. Now we know that, I mean, maybe I should call it phi n or something. I will change it to phi n. Okay. I mean, you have to change everywhere. So now we know that this goes to infinity. Okay, this I mean that integral whatever you have written, we have noticed that that supremum is infinity. So the proof of that proposition is over, and we know that supremum of norm phi n equal to infinity. Okay. So this implies that there exists, I mean, indeed, there exists a dense G delta set D contained in this C01, okay, such that phi nx, that is equal to Sn of f at 0. Okay, does not converge at all. Okay, so the Fourier series does not converge pointwise at 0, for example. It diverges for a dense subset of C01. So it's clear, no? Is it fine? Some reaction? Any doubt? I have proved that the supremum of all those linear functional is infinity by uniform boundedness principle. By uniform boundedness principle. Uniform boundedness principle. Okay. There exists a dense subset such that Sn of f. I mean, it's not point. I mean, it's not uniformly bounded, so it's not point-wise bounded also. So there exists a dense set f such that for all, I mean, there exists a dense G delta subset for all D for all f in D. I have time. If you want me to repeat something, I can repeat. Or if you want to give the essence of the whole thing, I can say it again. Then you can ask some question. Is it okay or it's not fine or I need some reaction? I'm only seeing myself. Is it fine?
Yeah, I think it's fine.
Okay. If it's not fine, you look at the notes. I have written everything, more or less everything clearly, at least this time. Okay. So you can look at the notes. And I didn't really follow any book for this. But if you just search the internet for uniform boundedness principle and Fourier series, you will get hundreds of notes for this. Okay. So I don't know which book has this. Okay. This is something standard I have been repeating each year, so I know it very well. Okay. So this is not from some particular book, but every book will have the same proof anyway. Okay. So I don't know whether Quest-7 functionalities book has it. I don't think so, but you can look at it. Okay. But many functionalities book, maybe Rudin has, I don't know. Okay. So if this is okay, I will stop recording.